Welcome back. And in this chapter, we're going to continue on the electronic structure of molecules. And now we're going to look at molecular orbital diagrams and how you can determine the electron configuration. And we're going to do this very similar to the way we build up electron configurations in multi-electron atoms using the Pauli exclusion principle. So if I start out with the case that we've already considered, which is the molecular hydrogen cation, then we know in this linear combination of atomic orbitals approach, we're going to take the atomic orbitals on the two hydrogens, and those are going to come together and they're going to form a molecular orbital that's lower in energy than the atomic orbitals, and it's going to form a molecular orbital and an antibonding molecular orbital. And I'm drawing diagrams here of what that wave function would look like. And you can see that there's a node here on the anti-bonding orbital, and this one doesn't have a node. And these are both sigma orbitals, so they have cylindrical symmetry about the bond axis. You'll notice here that this one has the G symmetry for Girard, so that means that this is the wave function is symmetric with respect to inversion about the origin, whereas this one changes sign, and that makes this one have the U subscript on it. So this is the molecular hydrogen cation, and if we had to write an electron configuration for that, well, we would just write sigma G1s in parentheses, and we put a little 1 up here, just like we would have written like 1s1. Here we're going to write sigma G1s, and then we're going to put all of that in parentheses with a little 1 superscript on it. And this is our electron configuration, and we've already worked out that this has a bond energy of about 267.8 kilojoules per mole. Notice that this has an unpaired electron, so this one has a spin multiplicity of 2 times half plus 1, which would be a spin multiplicity of 2, so it's a doublet ground state. Okay, so now we're going to move on to our first multi-electron molecule, and that's just simply going to be the H2 molecule. And in this case, we're going to have the 2 atomic orbitals come in, and we're going to form our bonding and antibonding molecular orbitals, and we're going to fill this up just like we would with atomic orbital configurations. So we're going to put the 2 electrons in the lowest energy state with opposite spin states, and we're going to write the configuration as sigma G1s and then a superscript 2 there. And of course, this one has a bond energy of 431, as you might expect, with the additional lowering of energy of that second electron. In the previous slide, notice that this one had a bond energy of 267 with this lowering in energy. And now with 2 electrons going down, we have a bond energy of 431. All right. Let's keep going. What about the helium molecule, so a diatomic helium? If you try to do this on an MO diagram, what you would find is you're bringing together 2 heliums, each has 2 electrons, so that's a total of 4 electrons. 2 will go into the bonding orbital, 2 will go into the antibonding orbital, and in the end, well, you could write a configuration like this, but this molecule is not stable because all of the stabilization you gain by going into this bonding molecular orbital, you lose because of the energy increase by putting the other 2 electrons in the antibonding orbital. So this molecule doesn't exist. But it does suggest to us that if we could remove one of those electrons in the antibonding orbital, we would get a net stabilization. And in fact, actually, the helium-2 cation does, in fact, exist. So if we would draw that, we would draw it like this, with the first 2 electrons going to the ground state to the bonding orbital and 1 in the antibonding. We would have this electron configuration, and that has a bond energy of about 251 kilojoules per mole, which sort of is consistent with what we saw with the hydrogen and hydrogen cation. Okay. So in this picture, then, you can see that the bond order is something that is analogous to the sort of whether we have single bonds, double bonds, and triple bonds, and so on. So you can see that if you took the number of electrons that's in the bonding orbital minus the number of electrons in the antibonding orbital and multiply that by half, you get a quantity called the bond order, which is similar to whether we're talking about single, double, triple bonds, but it's a little bit more detailed because you can see that in the molecular hydrogen cation, we only have a bond order of half, so it's not quite a single bond. In hydrogen, molecular hydrogen, we have a bond order of 1. You can see that for helium, diatomic helium cation, we have a bond order of half. And of course, for diatomic helium, we have a bond order of 0, and of course, it doesn't exist. Okay. We can keep going, move to the next row in the periodic table, and move to dilithium. And in the lithium diatomic molecule, we're going to have 3 electrons from each lithium coming together with a total of 6 electrons. So if we look at our diagram here, we're going to take our 6 electrons, put 2 in the 1s combination, so the sigma G 1s, 2 in the antibonding sigma U 1s, and then the next 2 we're going to go into the sigma G that's formed from the 2s orbitals of the 2 lithiums. So this gives us a net stabilization of 105 kilojoules per mole, and you can see that if you're calculating the bond order, well, these guys are going to cancel, and we're just going to have the 2 in the bonding orbital here, so we're going to have a bond order of 1 after we multiply 2 by half. All right. Now, similarly, you could look at beryllium. Beryllium is going to have 7 electrons, so bringing 2 berylliums together to make the beryllium diatomic, that has 8 electrons. But you can look at this diagram right away, and in the same way that we saw that we don't have diatomic helium, we're not going to have diatomic beryllium because it's not going to be stable. Now, it's also possible to form bonds using not just the s orbitals, but the p orbitals, that atomic p orbitals that are on the atoms that are coming together. So if we were bringing 2 atoms together and we're bringing them together along the z-axis, then the pz orbitals on each of the atoms can overlap and form molecular orbitals. So we can form 2 types of molecular orbitals. You can see as these guys, I have a picture here where they're coming closer and closer together, and they're constructively interfering, and we're forming a sigma type bond, so it's cylindrical symmetry about the bond axis, but it's formed from 2 p orbitals, and it's also symmetric about inversion, so it's G here for the subscript, so that's a sigma G 2p orbital formed from, molecular orbital formed from 2 atomic pz orbitals. Similarly, we can bring them together out of phase in such a way that we create an antibonding orbital. This has an additional nodal plane here between them, and that's antisymmetric with respect to inversion, so we have a U here, and that's formed again from the 2 p orbitals. So it's possible to form sigma bonds with p orbitals in addition to s orbitals. And in fact, actually, it's possible to form sigma bonds between s orbitals and pz orbitals too, as we'll see later. We can create another type of bond called a pi bond. This is something you probably remember from organic chemistry. If we have atoms that are coming together and we have px or py that are sticking perpendicular to the internuclear axis, then as the atoms come together, here, 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 you can see that we can get constructive interference between the p orbitals to form a bond that looks like this, which is what's called a pi orbital, a pi molecular orbital, and it's constructed from 2 p x orbitals in this picture here, and that has it's a U symmetry because when you do the inversion, you change sign here. So that molecular orbital from the 2 px orbitals gives us this, and we can also do it in an antibonding fashion, so we bring them together out of phase, and so we get a nodal plane between them, and that actually is symmetric with respect to inversion, so that's going to be pi g, but pi star g since it's antibonding, and it's constructed from these 2 p orbitals. Okay. So this kind of picture is probably something that you do remember from your, say, organic chemistry classes. These bonds do not have cylindrical symmetry about the axis, and that's the reason why we call them pi bonds and not sigma bonds. There's a nice web app by Paul Falstad. I just leave you the link here that you can click on and sort of play around with the different ways in which you can make these molecular orbitals and sort of vary the parameters a bit. Okay. Now, when we keep going with this picture, we're going to start looking at more and more electrons, and as we move across the periodic table. So we've done lithium. Now we're going to be moving on to boron, carbon, nitrogen, oxygen, and fluorine. When you get to oxygen and fluorine, the level looks like this here, and this difference between the s and the p orbitals is really high when you get to oxygen and fluorine because of the shielding differences for the s and p orbitals. And so we get this configuration here. But when you go down to boron, carbon, and nitrogen, what happens is that the distance in energy between these s and p start to decrease, and we get a little bit of bonding between the 2s orbital and the 2p z orbital, and that causes this sigma bond here to actually move up in energy here. So what happens in the boron, carbon, and nitrogen cases is that a little bit of this 2s bonds with this 2p, and in the final analysis, this sigma bond ends up being higher than the pi bonds here. But that's only in these cases. When you go back to oxygen and fluorine, this one is lower because the gap between these guys is bigger. And if you wanted to look at these across the rows there, you can see that here's lithium, beryllium, boron, that this would be the way the energy of that sigma bond would go as you moved across like this. All right. So let's take a look at boron then, knowing that we're going to have this switch here. So in the case of boron, then we're going to have now, instead of, we're going to have 10 electrons or 6 valence electrons that are coming together. And so when we put together the diagram here, we're going to do our normal filling up with the sort of Pauli exclusion principle and the building up rule here. And then we're going to put the last 2 electrons here in the pi orbitals, and those are going to be both spin up like this, as we would have done in an atomic orbital configuration. The ones that are the highest occupied orbitals, sometimes you'll hear people talk about those as called the HOMO, and the one that's closer to it in energy, the one just above it, is what's called the lowest unoccupied molecular orbital. So you might hear people talking about the HOMOs and the LUMO and the HOMO-LUMO gap in some particular situations. In this case, we get a stabilization because we can see that we have 2 in the bonding, none in the anti-bonding. These guys will sort of cancel out, and so we end up with a total bond order of 1. So 2 times 1, 1 plus 1 times 1/2 is going to be 1. And this case, then, we get a bond energy of about 289 for the diatomic boron. Keep going with carbon. You can see, we just add another 2 more electrons. So this was boron, carbon. We add another 2 more electrons. You can see that the bond order goes up. We're going to go to a bond order of 2. The bond gets shorter, goes to 124. It was 159 for boron. It's 124 for carbon, and you can see that because we have greater stabilization, they're pulled in closer together. All right. The configuration, again, just before, is going to just be these orbitals raised to the power, or sort of use a superscript here for the number of electrons. I forgot to mention that we stopped counting at some point here. We just look at the valence shell. So everything that represents the filled shell, we're just going to use the symbol KK to represent the filled shell down here. So for, in this case, the boron, everything below here we'll just call KK, and we'll just count from the valence shell up so that we don't have to create all these extra terms here. So in the case of carbon, then we're going to have this KK for the filled shell, and then we'll just consider the valence shell up here in the configuration. For nitrogen, add another pair of electrons. So again, look at this. This is boron, carbon, and nitrogen. We get another pair of electrons here, and it's paired. And this is the configuration here. And now we have a triple bond, you can see, because we have 1, 2, 3, 4, 5, 6 divided by 2 is a bond order of 3, which is consistent with what we know about nitrogen having a triple bond and a even shorter bond length of 110 picometers. All right. Now, oxygen is an interesting one. Keep moving across here because you see that we add another 2 electrons, and the electrons are going to go up here into the anti-bonding orbital. So now we're going to start to go back from a triple bond, as we were in nitrogen. We're going to go back down to a double bond, which is what we would have predicted, so a simple Lewis dot structure picture. But what the Lewis dot structure picture doesn't predict is the fact that oxygen is paramagnetic. It has unpaired electrons. So oxygen, if you have it near a magnet, will be attracted to a magnet. And if you have liquid oxygen, you can actually see liquid oxygen sticking to the poles of a magnet if you were, had it cold enough. So, all right. If we were going to go from these homonuclear cases to a heteronuclear case, we could still use the same approach. So if I take something like HF, we're going to take atomic orbitals on hydrogen, atomic orbitals on fluorine. We're going to bring them together to form a molecular orbital. Now, the ones that form the molecular orbital are going to be the ones that are closest in energy. So if you look at hydrogen and fluorine, the hydrogen 1s orbital is much higher in energy than the fluorine 1s orbital. So the fluorine, because of the higher charge of the nucleus, is going to be a much lower energy than the hydrogen 1s. And in fact, even the 2s is going to be lower. But the fluorine 2p orbitals will be similar enough in energy to the hydrogen that they can come together and have strong overlap and form these bonding and anti-bonding orbitals. And then, of course, the extra electrons would stay on the fluorine and the p orbitals there. All right? And this is how you might imagine sort of the bonding and anti-bonding orbitals coming together. And this would be our configuration here. And once again, we would predict a bond order of just 1 for the HF molecule. So that's it for this particular video. And now in the next video, we'll be looking at atomic orbital hybridization.